We will start with a little lecturing over, this will be our last lecture on static fluids. Static fluids, fluids that aren't flowing. In class tomorrow, we'll talk about moving fluids, flowing fluids as the term would be. And so last class period at the end, I talked about how high we could pull water up. And it turned out the height we could pull it up, we calculated, was 10.3 meters. Why was it only 10.3 meters that we could pull water up?
Because of the pressure inside, or the atmospheric pressure.
Okay, the atmospheric pressure is actually pushing it up, right? You can't really pull it up. But as you raise it, the pressure at the top goes down according to that delta P is rho GH. And when the pressure on top gets to zero, that's the lowest the pressure can ever get. You can raise the hose higher, and we stay at that level. But it's actually atmospheric pressure that is pushing it up. So one of the silly things I like to say is you simply can't suck something up a straw. What you can do is you can lower the pressure, and atmospheric pressure pushes it into your mouth. But it's the truth. Atmospheric pressure pushes it in when you lower the pressure on top. Now, when we make barometers, we usually make them out of mercury. Why do we make them out of mercury? What do you think what are some good guesses as to why they make it out of mercury?
Because mercury is denser and won't be pushed as far.
Okay, mercury is denser. Mercury has a density of 13.6, that's a 6, grams per milliliter. Whereas water is a density of 1.0 grams per milliliter. So it's 13.6 times more dense. How does that affect anything with the barometer?
It means it moves less far.
It means the height that you could pull it up is 113.6. So if we take our 10.3 meters divided by 13.6, that better give us 760 millimeters. Because 1 atmosphere is 760 millimeters of mercury. So a barometer is designed so you have a vacuum at the top and then a column of mercury that goes down to the water. And notice it shows in this picture the water going like this. It's not water. What is it? It says right there, mercury. Why is the mercury doing that?
Because its cohesion is stronger than its adhesion.
Because its cohesion is stronger than its adhesion, right. So it's the same idea as a meniscus. Oddly enough, their picture doesn't show a meniscus up here, but we can't win them all. They remembered at one point. So one reason to use mercury in a barometer is because it's much more dense. But there's another reason. A reason that's more technical in nature. You probably know that there's a certain amount of moisture in the air. We talk about the relative humidity and all that. Water pretty readily goes into vapor. And so if you have water and you have a vacuum of the water, you're going to have a lot of water molecules that go into the vapor, so it's not really a vacuum. There's going to be a pressure that's never zero at the top. Mercury has a much lower vapor pressure. Mercury is much less able to go into the vapor form. And when it does and you breathe it in, it makes you cuckoo, which is why Mad Hatters are mad, because of the mercury they breathe in, according to legend at least. So it has a low vapor pressure along with a high density, two things that make it good for a barometer, because if you made a water barometer, first of all, it'd have to be 10.3 meters tall. That would be annoying. And you'd have to worry about the pressure at the top not being absolute zero. And I'm not using the right app for that to have worked. Let's just move on. So the question here, which we're not going to do the woo clap, is why would you choose mercury? And the reasons are high density and low vapor pressure. It also conducts electricity and heat well, but those are not reasons you'd use them. Buoyancy, the topic du jour. Pressure increases with depth, right? We've learned that equation. Change in pressure is density of the fluid times G times the depth. So if you are swimming in water, the top of your body, bottom of your body, depends on who you are. Might be separated by a foot, might be separated by 4 inches. Let's take a foot. That's how many meters?
Like it's,
Let's say about 0.30. About 30 meters or 30 centimeters. What's the difference in pressure from the top of your body to the bottom of your body? Okay, the equation I just said, density of the fluid times G times the change in height. So that's going to be density of water, 10 to the third. I'm using kilograms per meter cubed just because that's the SI unit. 9.80 meters per second squared, 0.30. So if you multiply that through, since these are round numbers, let's just say this is 10, right? A lot of textbooks will do that. So I would have 3,000 pounds per square inch difference. Seems rather large, doesn't it?
That goes directly to pounds per square inch?
Or no, not pound. There's the problem. It's newtons per meter squared. Yeah, dude, that's much better.
Okay.
I was thinking, wow, that is just not sounding right. Yeah. So if you multiply these through, 10 times 0.3 is 3. 3 times 1,000 is 3,000. Wow, I can't believe I made that mistake. Because I use SI units, newtons per meter squared. So what does that mean? That means that the water at the bottom, what direction is the water at the bottom of my body pushing on my body?
Up.
Up. What direction is the water at the top of my body pushing? Down. So I'm going to have a net force. No, those are important questions. They may seem simple, but they're not trivial. So I'm going to have more upward force than downward force. So if, for instance, my body has an area, let's say the area of my body, if you were to cut it off and bend it over, it'd be close to a meter squared. So round numbers, we'll say it's a meter squared. So if area equals 1 meter squared, then if we look at force top and force bottom, the net force well, I better pressure bottom minus pressure top. And then putting the numbers we just did, 1 meter squared times 3,000 newtons per meter squared, that would be an upward force of 3,000 newtons. Now let's, taking round numbers, let's say a person has a mass of 100 kilograms. What is the force of gravity on them?
100 times 1.8.
Right. And so to round numbers, that's about 1,000 newtons, right? Using 10 again. So this person, this hypothetical person who, of course, is very light for their dimensions, would have an upward force of 3,000 newtons due to the water and a downward force of 1,000 newtons due to their mass.
Should they be floating?
Yes, they should float back up to the top. And so we call this force right here, this net force due to the pressure difference, the buoyancy. So that's the buoyant force. That's what we're working on when we're talking about Archimedes Principle. So here is a calculation to help us understand Archimedes' principle, and I will explain Archimedes' principle after I do this. Imagine that I have a cylinder in here in the water. Why a cylinder? Because it's an easy shape to calculate on. On the cylinder, so the cylinder is shown in dash, but let's imagine it's a real cylinder, real object in there. What direction is the force due to water pressure on the top? Down. What direction is the force due to water pressure on the left side?
To the right.
To the right, because it always is into the surface, right? So what direction is the force on the right side? And what direction is the force on the bottom? Right. So we have all of those forces due to water pressure. But notice the one on the left and the one on the right, they're in opposite directions. And you're going to have it at all elevations. You're going to have equal and opposite forces on the sides. So the net force due to the sides is going to be 0. The top and bottom, though, the pressure is different at the bottom than it is at the top, so it's going to have a net upward force that we call the buoyant force. And so to calculate that buoyant force, we are simply going to say, okay, the pressure difference is the density of the fluid times g times the height. And so and we call that the force buoyant. So that's where'd my brain go? Force, here's the mistake I made. Force is pressure times area, right? So I've got to do that times area. What is the height times the area for a cylinder? Volume. So that thing in parentheses is just the volume. So it turns out the force buoyant is the density of the fluid times g times the volume displaced. The volume displaced is the amount of fluid that's pushed aside. This problem, of course, was only for a cylinder. But it turns out that no matter what shape you use, that's what you're going to get for your answer. So the buoyancy is equal to the density of the fluid that it's in times the acceleration of gravity times the volume displaced. Now this brings us to, okay, question first.
What's the FLTP looking thing?
FL, that's fluid. I want to make sure we recognize it's the fluid because we're going to have two objects always. You know, if we're talking about floating or sinking or something, we're going to have two objects, one the fluid and one the thing that's floating or sinking. So Archimedes, the story goes, so let's see what we have in the two pictures at the top and how well they go with the story as I understand it. The king wanted a crown. And so the king took a certain mass of gold and gave it to a goldsmith and said, "Make me a most magnificent crown." And the goldsmith made a crown and gave it to the king. And for some reason, the king said, "I don't trust that goldsmith anymore. I think he might have cheated me." And so he comes to Archimedes, his trusted science advisor, and says, "I need you to determine if I was cheated or not, but you can't destroy the crown if I wasn't cheated." And so Archimedes is like, well, obvious thing to do. Let's measure the mass. If it's not the same mass as you gave me gold, then clearly he pinched some gold. So you measure the mass and it's the same. And he's like, oh, well, now what? Well, I'm going to take a bath while I think about this. And so he says, "Draw me a bath." And they draw him a bath. And he gets in the bathtub. And as he gets in the bathtub, what does he notice? He notices that the water level comes up when he gets in the bathtub. And he jumps out of the bathtub and he starts running through the town, yelling "Eureka," which nicely covers his, making it decent, because he figured it out. Eureka, by the way, is California's state motto. Which means I have found it. because he realized, hey, if I take the crown and I put it in fluid, it will displace a volume equal to its own volume. And so if I know what that volume is, I can calculate its density. Because what's density? Mass over volume. Yeah. The density is the mass over volume. So if the mass over volume is right and the mass is right, well, then it's got to be gold. And so that's what the story is about. Now, what's the outcome of all this? What is this thing we call Archimedes Principle? The buoyant force is equal to the weight of displaced fluid. Or the equation I already did. Density of fluid times the volume displaced. That's going to be the mass of the fluid displaced multiplied by G. So that's what we're going to be studying today to see if that's really true. So now let's go down and see if I have any more important pictures to go with this. Which condition is true only when an object floats? I have two questions here. And once again, I'm not going to have you pull out the phones, just too much time. Just blurt it out. When an object floats, which is true? And so we had one person said A, and one person says B, and one that said C.
I just know that.
Okay. It's always good to put people on the spot. So, Dr. Seth, if an object floats, which one is true? And of course, he hasn't looked at this for years, so.
So it would be B, but the weight of the displaced fluid is the weight of the object.
Okay, the buoyant force is equal to the weight of the fluid displaced. That's the rule, right? So that's Archimedes' principle. That has to be true. The buoyant force is equal to the weight of the object. If it's floating, it's in equilibrium, so the upward force is equal to the downward force. So both of those were true. Good job. Double thumbs up.
Wow. That's my teaching.
Okay, now another question. What condition leads to floating?
Oh, sure.
Okay, so let's just do, okay, we have two of them have to do with density, two with mass, two with volume. You said B, so let's look at what Archimedes' principle says. If I have something floating, the volume displaced is less than the volume of the object, right? Because if it wasn't floating, it would be the volume displaced is equal to the volume of the object. If it's floating, some of it's above. And so that means the force buoyant is equal to density of the fluid, volume displaced, times G. And the force of gravity on the object is equal to density of the object times the volume of the object times G, right? Mass times G. For the object, it's the volume of the object, not the volume displaced, and the density of the object. And if it's floating, what's true? Remember what Seth said just a minute ago.
And A.
Okay, he said the answers were B and A. He said if floating, then you have to have the net force is 0. So the buoyant force is equal to the force of gravity on the object. So I have force buoyant magnitude is equal to force gravity on the object, which means density of the fluid times volume displaced times G equals density of the object times volume of the object times G. Yes, ma'am. If it would be accelerating upward. So we can cancel those G's, and then let's just divide both sides by one of the densities. So, and one of the volumes. So I'll divide by, let's say, density of the fluid, volume of the object. So I'm left with an equation that says volume displaced divided by volume object is equal to density of the object over the density of the fluid. Now we can answer this because we already have a relationship. If I divide both sides by volume of the object, I have the volume displaced divided by the volume of the object is less than 1. That's a condition for it to float. So that means the density of the object over the density of the fluid is less than 1. Or the density of the fluid is lower than the density of the object. What?
No.
Yeah, okay. I was like, I said that, and I'm like, wait, no, that's not going to do it. Density of the object is lower than the density of the fluid. So for an object to float, it has to have a density lower than the density of the fluid. So if you take a ping pong ball and you drop it in, I'm not going to drop in that one. You drop it in the water, the fact that it is floating means that its density is less. And you can see that most of it is above water level. Why is most of it above water level?
Because it's far less density than water.
It's far less dense, so you have to have the weight downward is equal to buoyant force upward. The buoyant force upward has to do with the volume displaced. And so it's displacing a volume of water that weighs the same as that ping pong ball, and there's not much volume of water to weigh the same as that ping pong ball. So it's displacing very little water. Maximum.
All right, quick question.
Yeah.
Can something have a high density but low viscosity?
Viscosity is a measurement we'll come to in the next chapter before the test still. This test is covering the lecture tomorrow. Viscosity is not directly tied to density, although it surely seems unlikely that low viscosity means it flows really easily. And so low viscosity you would assume goes generally with less dense materials. But that's all I can really say. This is, by the way, just a definition that is fairly trivial. Specific gravity. Specific gravity is just density divided by the density of pure water at 3.98 degrees Celsius. I've been approximating that to 4 degrees Celsius for the last couple days. But 3.98 degrees Celsius is the temperature where water is the most dense at 1,000 kilograms per meter cubed, or 1 gram per centimeter cubed. So specific gravity is the same as density in units of grams per milliliter. It just doesn't have units. So I suppose I could ask, something has a density of 4.28 grams per milliliter. What's its specific gravity? It's the same number. A simple problem here, given that we have lab and we're going to be doing things with the lab, I'm not going to do the problem. And instead, we're going to go straight to the lab. And the lab is also in this app. So for the lab, we're doing Archimedes Principle. And the important equation for this lab is this equation right here. The buoyant force is the density of the fluid times the volume displaced times G. So we are going to check and see if this is correct. So first, your scientific method. Your observation must relate to floating and sinking. So I observe ping pong ball floats in the water. Right? It's something that simple. And then it has to be something that's testable readily. Now, it doesn't have to be testable here in the laboratory. If you have some other place and thing you want to do, like go to the swimming pool and, whatever. Why do leaves eventually sink? It's somewhat germane.
They like get absorbed, soak up the water.
That's
Yes.
what I was thinking.
Which means not cold.
Okay, so moving on. For your test, use a floater. Some things will sink in water, some will float in water. Use something that floats in water for your test.
Oh,
How's that feeling in the sun?
What was that?
How's that you feeling in the sun?
Yeah,
What?
Because I was seeing something in the sun.
Yeah.
I still didn't understand you.
I thought it said it used.
I thought it said both. It said either way.
I thought we were supposed to use something that sinks.
Yeah.
Everyone has to do one trial with something that sinks.
Oh.
And then for your test, do it with something that floats.
So the test, like for that observation,
For the test of your hypothesis.
scientific method.
Yeah.
So what if I use ice?
Ice floats.
So I can. I mean, do you have ice?
Assuming that they have the ice machine fixed, yeah.
So we can use that for a test.
Yeah.
We're done.
Okay, that was exciting right there. Okay, so what are you doing? Let's just go through the steps. The first step is connecting up the hardware. Well, I've connected. We're using this kind of force sensor. And it tells us to, okay, you're not using the scientific 750, you're using the 850. So it tells us to connect it up to make sure that we have the sensor set at times 10 sensitivity. I think these ones have the sensitivity. No, these ones don't. Okay. Maybe it's in the software. And then we calibrate it. So let's go to the software and do the calibration. So actually, first, how do I know that it's not working?
Because it's thinking. It
And
has
how's
a
that
little-
thinking?
That yellow triangle.
Not that too.
The yellow triangle means it's not detecting anything. And of course, the reason was because I hadn't plugged it in. Now it's detecting stuff. No, I'm not going to update the firmware right now. I'm going to click on the thing here for the force sensor just to see high resolution force sensor, blah, 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 blah. Yeah, nothing there to do. Okay, but I need to calibrate it. So I go to calibration, choose the type of measurement you'd like to calibrate. Force sensor. Shocking. Next. And choose the probes you would like to calibrate, whatever's that. You want to leave it here on the 2 point. Next. And then we're going to have two values, a standard value, and the first standard value I'm going to have is with nothing on it. Now, instead of accepting it as is, I come out here and I press this button that says 0. It might say tear in your lab guide because the older version said tear instead of 0. But what that did is it changed it. So you see the lower number that's bouncing around a little? That's pretty close to 0 now. That's what pressing that button did. Now I just click set current value to standard value, and it brings up the second one. So my second standard value, I take my 50 grams, and I hang the 50 grams from here. What's the weight of 50 grams?
0.49.
It's 0.49, whoops, up here. 0.49, so I need to put 0.49 here so it's properly calibrated.
Yeah, it says so like laughing.
Oh, it says that?
Yeah.
Well, remember, force of gravity is mg. So 0.05 kilograms times 9.8. So I set current value standard, and now it's calibrated. Make sure you do hit finish. Don't hit cancel or else it will forget all of your calibration work. So that's how you calibrate it. Any questions on the calibration? So what units is it calibrated in? Newtons. All right, so now I'm ready to do my experiment. Let's go back and read the instructions rather than me freelancing it. So, yeah, it says 0 or tear because of the 2. Then click finish. Each student should select, and personally, not as a group. So you can have 6 people in your group for this one. I don't care. It's just more work. So let's suppose that these 3 people decide we're going to be a group of 3. So Sarah picks one object, Anna picks another object, Aaliyah picks a third object. They have 3 objects, and each person does all the measurements for one of those objects. And then you record my data, make a data table, have one column my data, one column, Aaliyah's data, one column Anna's data. So you have to have all of the data for everyone in your group. And you're going to take an object. So I choose an object because I'm fundamentally lazy. I'm choosing an object that already has a string attached to it. So I take this object, and I'm first going to measure its mass when it's in air. So before I hang it on here, just because these things sometimes drift a little, I hit 0 before I hang it on, not after. Put this on here, still so it doesn't swing, and then I'm going to measure what the weight is. Notice it has a number, then you can see it varying. So I can look at this and say, okay, that should be 1.024 plus or minus 0.002 newtons. Right? It's pretty clear how much it's varying and where the average is. But I could also, the reason I have the graph is I can go to the graph, turn on the statistics, and the mean is 1.024, nailed it. Standard deviation is 0.002, nailed it. So I can get those directly from the graph. Now, in this case, because I had it stationary the entire time, I didn't have to select what part of the data I was analyzing. If you had this was running and then you hang it on there, you need to make sure you select the right part or else you're going to get nuisance and useless answers. So that's part 1, part 1A. Part 1B is I measure the volume of water in my graduated cylinder. And for every trial, make sure you measure the volume before, because for each trial, you're going to take a little water out. And so the volume is going to slowly be dropping as you go through the experiments. So I read this very carefully. When you have a meniscus, where do you read? The bottom of the meniscus, the flat part of the meniscus, to be really clear, because if it was mercury, it would be the top of the meniscus. So I read on this, and it's above 350. It's 1, 2, looks right on the 3rd line. Here's the question that, if people make mistakes, it's the biggest one they make. The markings on here, between 300 and 350, it has 10 markings. So what is the size of one marking?
5.
5. So that means it's 315 point, well, can't really get a point. You're estimating to 1 in that last digit. So plus or minus 1, I'd say, 315 plus or minus 1 milliliters. Or centimeters cubed, because the centimeter cubed and milliliter are the same thing. So that's part 1B. Then we go to part 2. Part 2, I need to put this so it's completely submerged and not touching the sides. Right now it's not in it at all, right? So easily remedied. Easily coordinated, I should say. Okay. So now it's completely submerged, not touching the sides. Now I repeat both measurements. So I'm going to measure what the force necessary to hold it up is now. And it's 0.905 plus or minus 0.001. It's dropped, right? 1.024 to 9.05. And then I measure what the volume shown by the water is. So the water shown by the volume is 1, 2, 3, about 4, almost 5. So I'd say 324 plus or minus 1. So now based on those numbers, and of course I didn't write any down, so I hope I remember them right. I had
1.024.
Plus or minus.
0, 0.
That was a plus sign. Trust me. Okay, so there's the measurements I had for this object. So everyone's going to take, you notice that didn't take a lot of time, right? But you have to know what you're doing. And so it's not going to go quite as fast for you the first time. So now that I have that, let's look at the things I'm supposed to do with it. What material is your object made of? Well, this object here, now that I'm done, I can take things apart. This object here may or may not say what it's made of. I can tell you what it's made of based on what it looks like, but sometimes they have stamped on them. If you don't know, and you can't figure it out, ask us. So this doesn't say what it is, but what is it? It's copper. So this is a copper object. Copper. Find the density of the material. How am I going to find the density of copper?
Online.
Okay, so I go to Google, my friend Google. I look up density of copper, and you need to make sure you have a reference for where you get it. So, like if I just take this, I don't have a reference there. That's not going to work for me. But I can say, okay, it came from Ames Web. So let's go to Ames Web just to make sure what it says there. And you see, oh, there's a whole bunch of different alloys of copper. Oh, the pain, right? Does it have an average? No, it doesn't even have an average. So looking at this more carefully, I'd say, wow, it's somewhere between 7.53 and 8.94. And so I might record that range, or I might have been lazy and just said the number that it showed on Google search was just the top one. The oxygen-free copper, that's pure copper. And that probably is the one that it's most likely, but it could be some alloy. But make sure you give a reference for where you got that number from.
For the reference, could we just say amesweb.com?
Yes. I mean, make sure you give it so somebody could verify. Okay, then find the error of difference between density you measure and the accepted value. Well, what's my density?
Got to do that calculation.
Got to do a calculation. So I have the volume is equal to volume 2 minus volume 1 is equal to 0. 0 to 9 plus or minus 1 milliliter. Now notice that plus or minus 1 means 11% error. And I might be a little optimistic in my error. So I know that 11% would be as good as dead on. And then my force buoyant, is equal to F1 minus F2, which is not what I need right now, but I'm still going to calculate it. So if I subtract those, that's 0.1. So that's my buoyant force. And if I want to find my density, the force in air, force 1 is equal to density of the object times volume of the object times g. So the density of the object is equal to force 1 over volume object times g equals 1.024 newtons divided by, okay, so I had 9 milliliters. A milliliter is 10 to the minus 3 meters cubed. If I remember right. And that should give me my density. So real quick, since we looked it up, what do I get when I calculate this? we'll find out right away if I'm wrong in my conversion of units.
11.61.
11.61. Really?
Yeah.
Not newtons per meter cubed, kilograms per meter cubed. Then I must have made a mistake, because that would be the value in grams per centimeter cubed, not in kilograms per meter cubed. So this must be 10 to the minus 6 then. You sure you put 10 to the minus 3 there?
I did.
Okay. So it must be 10 to the minus 6. Here's how I always,
11,609.18.
yeah. Yes. Yeah, that's what it should be. 11,610. If we do the conversion, 1 milliliter is equal to 1 centimeter cubed, right? And then if we take a centimeter cubed, we multiply by, and sure enough, that's 10 to the minus 6. So that's how I always go through the unit conversion. Obviously, you can look it up as well. Okay, so what's my percent error of difference? You take the absolute value of the difference between your measurement and the theoretical, divided by the theoretical, and multiply by 100%. Am I within 11%? Not hardly.
You're
Right. I am about
30%.
Yeah. So what I see here and what you're going to see is you're not going to have super precise measurements. The reason is the uncertainty in this. I was a little optimistic with my plus or minus 1. If I'd had plus or minus 3, it probably would have been a little more reasonable. So I've already told Andrew for his grading, there's going to be bigger percents error here because you simply can't measure that volume as accurately as you'd like to. Back to the instructions. So we found the percent error difference between the density I measured and the accepted value. Compare the measured buoyant force, the weight in air minus the weight in water, to the buoyant force predicted by Archimedes' principle. Well, I've already calculated the buoyant force was 0.119 newtons. What's the predicted by Archimedes' principle buoyant force? So if I put the density of water is 1 gram per milliliter. The volume displaced, 9 milliliters, times G, 9.80 meters per second squared. And then, of course, I'm going to have to convert it to newtons, so it's a factor of 1,000. So what do you get?
That times that, or divide by 1,000,
Yeah, this divided by 1,000.
you get 0.0882 newtons.
So the predicted buoyant force, according to Archimedes' principle, 0.0882 newtons. The actual measured was 0.119 newtons. You can see there on the left. And of course, that percent error is probably going to mirror the percent error I had on density because they're using fundamentally the same numbers. Based on your measurements, what conclusion can you draw about Archimedes' principle? Based on my measurement, what conclusion can you draw?
It's not very accurate.
Okay, my measurements were not very accurate, so it's within shooting distance, but this is only one trial. You're going to have a minimum of 3 trials when you're done, right? If you have 2 people in your group, you have each one with your sinker and then one with the floater. So you'll have 3 trials, and then you can draw a more general rather than based on one data point. That's it. Any questions?
Okay, so we do, for both people, we do one sinker and one floater.
Incorrect. You do one sinker for everybody in the group.
Okay.
You do one floater for the entire group.
Okay. So where do we find said floater?
So I have all of the findings up here. So what floats? Wood floats. So I have some wood things. And then I have what sinks, everything that's not wood.
Gotcha.
I think the rubber stopper sinks. Showed up. So yes,
Don't infect yourself.
I also have some cork, which also floats.
Oh my god.
All right.
Okay.
That's too big.
So you said what, 2 sinkers, 1 floater.